This video is brought to you by Nebula. Watch our bonus videos with F-16 test pilot David Kern by signing up to Nebula for only $250 a month. A fully loaded F-16 is a force to be reckoned with. An air superiority machine that countries the world over use to patrol their skies. A low-cost, lightweight, single-engined fighter specifically designed to outmaneuver its opponents while carrying state-of-the-art missiles that would, hopefully, mean it would never have to. The F-16 was born out of the Vietnam War. Large, heavy, complex US fighters like the F-4 Phantom were the norm, but the F-4 found itself in peril frequently, at a significant disadvantage when taking on the smaller, maneuverable Soviet-made MiGs of the Vietnamese Air Force, like the MiG-21. The MiG-21 was a small, single-engined, lightweight aircraft with thin delta wings. The F-4 was fast, flying up to Mach 2.2, travelled further, and carried more missiles, with a powerful radar. But its lack of maneuverability at low speed, poor pilot visibility, and easy identification due to jet engines that billowed black smoke trails made it vulnerable to sneak attacks from the Soviet interceptor. MiG-21s frequently flew close to the ground, under radar, and ambushed incoming F-4s, making a single attacking run with their ATOL infrared guided missiles, and then using their low-speed maneuverability to outturn and escape. From August 1967 to February 1968, US losses in Vietnam were staggering, losing 18 aircraft while downing just 5. For a nation accustomed to absolute air superiority, something was off. The MiG-21's introduction in 1966 forced the US to adapt. Its large heavy fighter bombers, while useful, were at a disadvantage against these smaller, cheaper planes, and something needed to be done. The Red Barn study, commissioned by the US military, began to identify and address the tactical and technical issues causing the heavy losses that both the US Navy and Air Force were experiencing in the Vietnam War. And their findings led to the development of one of the world's most ubiquitous fighter planes, a plane designed with a new, physics-based doctrine at its core. Entering service in 1978 and standing the test of time, it is now confirmed that the aircraft will be entering the battle for Ukraine's freedom, taking on the modern-day counterparts of the MiG. This is the insane engineering of the F-16. The F-16 was built from the ground up with this classified 1966 paper as its guiding light. A paper full of mathematical models, graphs, and equations designed to answer one question: how to win a close-quarters dogfight. Created with the help of military supercomputers, it defined a new concept: energy maneuverability. Created by Colonel John Boyd, an Air Force veteran of the Vietnam War and one of the members of the so-called fighter mafia, with the help of a civilian mathematician, Thomas Christie. These graphs were the basis for defining a plane's maneuverability through its full range of speeds: Mach number on the x-axis, turn rate on the y. A theory underlined by the management of both kinetic and potential energy, speed and altitude. In order to change direction, a fighter aircraft must trade energy from these reservoirs, and doing it as efficiently as possible is the key to outmaneuvering an enemy. This is the energy maneuverability diagram for the F-16. It's a complicated graph to read without some basic understanding. This line is defined by the maximum lift of the aircraft. This is important because it determines the maximum turn rate at a particular speed in this region. We need lift to turn. To begin a turn, an aircraft will roll in the direction of the turn. This splits the lift the plane is generating into two components: a horizontal component that causes the plane to turn, and a vertical component that keeps the plane in the sky. A steeper bank angle will increase the horizontal component and increase our turn rate, while stealing lift from the vertical component. This vertical component needs to equal the weight of the aircraft, or the plane will lose altitude. To compensate for that, the pilot will need to increase lift by increasing the angle of attack. This is where the maximum lift issue arises. More lift means more available force to turn. To determine the max turn rate for an F-16 at 0.4 Mach, we simply draw a line straight up and across to our turn rate, 13 degrees per second. Now this is where things get interesting. This is the graph for an F-4E. At the same speed, the F4 can make a maximum turn of just 5 degrees per second. To determine a sustained turn, we look to this line labelled with a 0, meaning no loss of altitude is required to make the turn. We can see the F-16's best sustained turn is 14.2 degrees per second at 0.85 Mach at 7G. The F4's best sustained turn is 10 degrees per second at 0.85 Mach at 5G. This is what that looks like in practice. It takes the F-16 25 seconds to complete a full 360-degree turn, while it takes the F4 36 seconds, 11 seconds in the difference. The F-16 was a radical new way of thinking about fighter aircraft, and that design philosophy can be seen with how the engine inlet has been designed to deal with supersonic flow. To learn more about the F-16, we spoke with an F-16 test pilot.
So the F-16 inlet is one of those things that tells you about the design philosophy of the aircraft. Because up until that point, the thought process was we wanted to go faster, we wanted to go higher. And nobody stopped to ask why. Because it turns out that not a lot of fights, not a lot of air combat was happening in that Mach 2 plus range. In fact, very little of it was happening, and it didn't have a huge amount of tactical application. And so as John Boyd and the rest of the team was looking at this lightweight fighter design, which became the F-16, they said, well, where do we think that the dogfights of the future are really going to happen? And they said, well, it's probably going to be somewhere in that 0.8 Mach to 1.2 Mach regime. That's really where we need to be in terms of optimizing the performance of the jet. And we see that here in terms of the specific excess power chart, where it's got this advantage right here in that range of 0.8 Mach to 1.2 Mach. That's where the fat part of the chart sits. That's where you're fat on energy. That's where you have that advantage. And so the F-16 propulsion system is not optimized to go over Mach 2, although it can. And I've flown the F-16 at Mach 2. You run out of gas pretty quick, but you can go that fast. But in that, what we call transonic regime of 0.8 to 1.2 Mach, you've got a different design problem than some of the previous jets. And you can see that in terms of the inlets. The inlets on the F4 have this extension that goes sort of along the cheeks of the aircraft forward, and then the actual inlets are set back. And what that's designed to do is attach a shock wave to the front of that inlet lip, and then it goes backwards and expands along the body, and that shock wave is basically going to cover up the inlet. That has some thermodynamic effects in terms of pressure recovery for the fan face, because you don't want supersonic air getting all the way in to your turbine. If you have supersonic airflow hitting the front face of that jet engine, the jet engine is going to disintegrate. It's designed to ingest subsonic airflow, and so you have to attach that shock wave at the front of the inlet. That's part of what slows down the airflow to eventually a normal shock inside the inlet. It expands a little bit, and then it gets to the front face of the compressor, the fan face of the compressor. Well, the F-16, and you can see it right here, has what we call a pitot inlet. It's basically a flat face air scoop. It is not that sort of overhang with a lip and then an inlet that's further back, like you see on the F4 or the F-15 or the F-14, the MiG-29, the Su-27. All of those have more of that inlet that's set up to put an oblique shock wave across the front of the inlet. Those are designed to go faster. The F-16 has a little bit of that. If you look at it on a side view, you can see how it's got a little bit of an overhang on the lip, and the nose helps to attach a shock wave. But it's not as efficient to go above Mach 1.2, and that's okay, actually. It can go that fast. It can go faster, but the engine is working a little bit harder as it gets into this 1.4, 1.5 Mach range compared to something like an F4 or an F-15. That's where they start to really stretch their legs and run.
These designs for optimizing maneuverability at these speeds can be seen elsewhere too. its air intake placement underneath the aircraft, a stark difference to the side-mounted twin intakes of the F4, and the thin, elongated wing that blends smoothly into the fuselage with these wing extensions forward of the main wing. These are called leading edge strakes. This air intake ensured the F-16's engine was not starved of air during high angle of attack maneuvers, with the forebody of the aircraft helping to funnel and divert air directly into the air intake. However, this does come with some problems that needed to be engineered around. On takeoff and landing, this air intake is only 100 centimeters off the ground. This, combined with the extremely thin wings, made placement of the landing gear difficult. The forward landing gear could not be mounted ahead of the air intake, as it would kick up debris into it, and they couldn't fit into the wings either, as the thin, aerodynamically optimized wing didn't have enough space. The F-16's landing gears are stored just behind the air intake, and in order to provide enough stability and bracing on landing, they need a unique folding mechanism to swing them outward to create as large a wheelbase as possible. The front landing gear, which is steerable during taxi, also rotates 90 degrees to lie flat just under the engine inlet. Above the inlet is a boundary layer diverter channel. This ensures the engine gets consistent laminar flow. As air travels along the length of the aircraft, a layer of slow-moving, turbulent air called a boundary layer. If this air is allowed to enter the engine,